So good morning everyone and welcome back to our MSD 780 lectures. So today we're quickly going to look at section 5, the kinematics and inverse dynamics of the driven pendulum rod. So this is the last part that we want to do before we're going to jump into the DAP-BC. So just to perhaps make a quick distinction between what we did in the previous lecture and what we're going to do today. For section 4, I've just added this undriven pendulum rod analysis section or statement over here. Reason being, for that case, the only force that actually worked in on that pendulum rod was weight. So we didn't apply any driver or motor constraints over there to alter either the kinematics or the dynamics of the system over there. For today's lecture, however, we're going to look at the kinematics and inverse dynamics of a driven pendulum rod. So in this case, we're going to have some driver constraints, which means that we're going to have different accelerations depending on what the input moment, the input torque is on the system. So once again, we can distinguish between a kinematic analysis and then also an inverse dynamic analysis for this system. Inverse dynamic analysis in the sense that we're going to prescribe some sort of an acceleration for the system, and we then want to measure what the resultant torque on the system is going to be. So once again, for the kinematic analysis, just to iterate on what it is, over here we said that a kinematic analysis by definition is the solution of the coordinates, the velocities, and the acceleration of closed chain systems by solving the constraint equations. Now, when kinematic analysis is considered for a mechanism that has a single degree of freedom, like in our case where we have the pendulum rod, we know that the pendulum, the only degree of freedom that we have over there is the actual rotation of the rod. One driver constraint is included in the formulation. And based on the motion described by the driver, the kinematics of the entire system can be solved for. So for a kinematic analysis, we define as many driver constraints as the number of systems degrees of freedom that we have. So this general statement of kinematic analysis can then be applied to any system with one or more degrees of freedom. And to perhaps illustrate this, we can look back at our example for the pendulum rod. And in this case, you'll see that our pendulum rod changed a bit. Previously, we just had this weight acting over here with its components. Now we have some sort of a torque or a moment that we're applying over here at the joint as well. And this is then going to affect the acceleration and the overall dynamics of the system as well. So the number of degrees of freedom, in this case is 1. We said that that's the rotation of the system, and the number of defined coordinates is 3. And to perhaps just illustrate what we mean by that. So regardless of the choice of the coordinates, for a multi-body system with n subscript DOF degrees of freedom and n subscript V defined coordinates, if NV is greater than n DOF, then there must be NC, so n subscript C, which is equal to the NV minus n DOF independent constraint equations. So if we illustrate this with our current example, we can see that the coordinates that we want to take into account is the X and Y translations and also the rotation of the system, which is phi1. So in other words, NV is going to be equal to 3. And we know from the previous analysis that we did that our number of degrees of freedom is also 1. Okay, so if we then scroll down, we can then go and calculate how many independent constraint equations we have. So NC is once again equal to NV minus n DOF. So we have 3 coordinates minus the 1 degree of freedom. So we need 2 independent constraint equations. And we actually already have one of these from the previous analysis that we did. So this is this phi q that we have over here, which is equal to minus R1A. Something that I just want to point out over here is for the calculation of this R1A. So in other words, the global location of point A on body 1, we can see that some of the criteria that we need is the actual coordinates of the body. And then we also need these local coordinates of that point on the body. So this psi 1a and eta 1a. And then we also need phi 1. And this is going to be important when we apply this in the DAP-BC workbench later on. These are the things that we're going to specify for each body in order for it to calculate the location of the points. Okay, we can simply go and rewrite this in this form as well. So if we combine the transformation matrix with this local coordinate vector over here, then we can simplify it a bit as well. It also follows then that we will have to specify one additional driver constraint for the driven pendulum rod. Now, if we go back over here in a general formulation for kinematic analysis, if Q denotes an array of NV coordinates, then NC position constraints and NDOF driver constraints are formulated according to equation 12.1. So in other words, what this shows us is that if we look specifically at these driver constraints over here, we can express our driver constraints as a function of time. And that's what we're going to do as well when we look at the second example of our pendulum rod. So for our given pendulum rod, phi q has already been defined, and the single driver constraint is given by this function that we have over here. So this is, I think, maybe jumping the gun a bit, but we're going to look later on at the actual example that we have over here. We just specify an acceleration for the system, which is 2 pi over 60 radians per second squared. And from there, we can actually integrate it twice to get the rotational velocity and then also the position or the rotation angle of the system. Okay, so we know that phi q we get from this equation over here at the top, and then phi of the driver constraint is what we will have to denote or deduct before we go into the DAP-BC analysis. As we have already seen in chapter 7, driver constraints are simple functions of one or possibly two coordinates and the parameter time. So the first and second time derivatives of equation 12.1 yield the velocity and acceleration constraints. In other words, we simply take these two equations, 12.1, and we derive it once, so then we get this matrix-based equations over here. And in this case, we know that D denotes the Jacobian matrix. And then we can just extract Q dot, so that will be our velocity vector. And over here for the driver constraints as well, we know that it's going to be a function of time, so we're just going to derive that function of time to get it in relation to the actual velocity. For our driven pendulum rod, equation 12.2 therefore becomes this equation that we have over here. So we can see it's once again a combination of what we had for our independent constraint and then our driver constraint as well. And we can just set that equal to a function of time over here for the driver constraint. So this is this last line that we have over here. Okay, and then once again we can derive it again, and then we end up with the acceleration data that we need. But what you'll notice is that at the start these two matrices are the same, and this is quite a powerful and a good advantage of the DAP-BC workbench that we have, or the body coordinate formulation that we apply, in the sense that if we step across our derivatives, this Jacobian matrix over here remains the same. So it makes it easier to solve, of course, from a numeric perspective. So you wouldn't want to go and perform these calculations by hand, but in a numerical environment, it's quite effective. So for our driven pendulum rod, equation 12.3 then becomes these equations that we have over here. So you can already see that for a very simple pendulum rod, we already have fairly complex equations that we need to go and solve. So doing this by hand would become quite tedious, especially if you now have a 2 or 3 multi-body mechanism. However, we can go and simplify this a bit. So once again, it's we have this Jacobian matrix over here, and then we just set it equal to whatever we have on the right-hand side of 12.3 over here. Okay, so the coefficient matrix in the velocity and acceleration equation is square, so that's just important to note as well. What we mean by that is, I think if we go back to this one, we can see that it's a 3x3 matrix over here, which we multiply by our acceleration vector, and then we have a similar, or actually exactly the same matrix over here for our velocity calculations. Okay, so any questions so far on this? Right. So the objective of kinematic analysis is to solve these algebraic equations for the coordinates, the velocities, and the accelerations for a specified time period at delta t time intervals. And if we look over here, there's an algorithm that breaks this up. So we sweep the time parameter from t equal to 0 to t equal to tn by increments of delta t. And at each time step, we set t equal to ti, and we perform the following steps. So we first solve equation 12.1 for q, so our coordinates. Then we solve the velocities through equation 12.2, and finally the accelerations through equation 12.3. And then once we have all of that, we can compute the coordinates, the velocity, and acceleration of any points of interest on these bodies. And if you're more interested in that, you can go and look at example 12.1. This is a fairly straightforward example as well of how they apply these parameters and this algorithm to solve the problem. Okay, so then for section 12.1.1, which is the solution procedures, the kinematic analysis requires solving the kinematic and the driver constraints at a given time, t equal to ti, for the coordinates, velocities, and accelerations. So the position constraints are in general non-linear algebraic equations, but the velocity and the acceleration constraints are linear in the velocities and accelerations. Whether we solve linear or non-linear equations, we may consider two possible arrangements for these equations. And our first arrangement that we have over here, we can consider a set of two equations, but we have three unknowns. So these are equations A over here, so x plus 2y minus z equal to 2. And then we also have 2x minus y plus z equal to 3. So for our driven pendulum rod, we had that x1 is equal to this expression over here. This is simply relating the local coordinate system to the global coordinate system for x and y. And if we then assume in this equation A that the value of one of the unknowns are given, so this is z equal to 3, then we can actually go and substitute this in, and we will then end up with a system of equations where we have two unknowns and two equations. Okay, so for our driven pendulum rod, once again, we have this phi1 as a function of t that we express over here. We're going to look in a moment how we got to this equation over here. But equation A may be considered as two kinematic constraints, and equation B may be viewed as a driver expression, or driver constraint equation without the presence of the time variable. So our first arrangement is that the value of z that we obtain from equation B can simply be substituted into equation A. So then we end up with these two equations. We can write it in matrix form, and we can solve for x and y. So this arrangement is then known as the coordinate partitioning method, or CP method. The second type of arrangement that we have is equations A and B are considered simultaneously to form three equations in three unknowns as follows. So in other words, we simply express z equal to 3 as a combined equation together with these two equations that we have over here. We can express that in matrix form, and we can solve for x, y, and z simultaneously. And this arrangement is then known as the appended constraint, or AC method. So alternatively, for our driver pendulum rod at time t, we can formulate the following three equations, which we can solve simultaneously. So these are the equations that we got for the transformation from the local coordinate system to the global coordinate system. And that is then done for x and y. And finally, we have our driver constraint over here as well, which is a function of t. So we just write all of that on the left-hand side so that we have zeros on the right-hand side. Okay, and this is then the set of equations that we end up with if we start if we start simplifying it. So although, yes.
Quantitatively, more just a locator along our pendulum.
Yes, yes, that's correct.
So spine intervals, let's say you're interested in the point at the end of the pendulum.
Yes.
You said, depending on how you set up your coordinates, your psi would be here, and your eta would then be the length of your pendulum.
Yes, so if I can perhaps show you an example. So I opened this pendulum rod over here. So what we're going to use for the DAP BC and our body coordinate formulation is to always place the psi eta coordinate system at the center of mass. So when we want to locate those points, we just reference them with respect to the xi eta, and we'll do that on the body itself. So you'll see. Yes, yeah. So you'll also always know where the coordinate or the center of mass is located. Yes. Okay, so although the two arrangements are not very different, from the programming and computational points of view, there are advantages and disadvantages associated with each other. So this is illustrated in example 12.2, but in the coordinate partition method, the number of equations and hence the number of unknowns is smaller than those in the appended constraints method. So therefore, the computational effort with the CP method is less than that of the AC method. However, for developing a general purpose kinematic analysis program, the programming effort that the AC method requires is much less than that of the CP method. And it also becomes now more efficient in the sense that we don't have to calculate these things by hand. So in other words, we can just give it as input or an input algorithm to the numerical system and it will solve it in any case. So this is due to the fact that the AC method, the constraint equations keep their original forms. So we do not need to split a set of equations into the known and unknown parts and move the known parts to the right-hand side. That's not necessary. We can have everything on the left-hand side as we saw with the AC method. Another important point is that in problems with a large number of equations and coordinates, appending one or two driver equations to the original set will not make much difference in the computation time. So therefore, in most general purpose programs, we would rather want to adopt this AC or appended constraints arrangement. Okay. Yes.
Does that mean that for the CP method, you'd have to, let's say you're adding a new type of constraint, you'd have to redo
yes. Yes. So since you're substituting it into your already known constraints that you have available, you would need to go and reevaluate those initial constraints that you specify. So it's much easier to rather just add to a matrix and then from there solve it again. So from a computational perspective, it will probably run a bit longer, but at the same time, it's much more efficient than having to first do these calculations by hand and then carry it over to the computer program. Yes. Yes, definitely. Yeah. Yes.
Program equation. Your matrix as it is, even though you have constants.
Yes, that's correct. Yeah. Right. So then the velocity and acceleration constraints, whether we arrange them for the coordinate or the constraint, what is this, the CP method and the appended constraint method, are respectively linear in the velocities and the accelerations. So solving these equations for the velocities and accelerations requires solving simultaneous linear algebraic equations in the form AX equal to C. So the solution to a set of simultaneous linear algebraic equations using the backslash operator, I believe this is similar to the Gauss elimination method that MATLAB uses, is discussed in PMD section 2.3.2 if you want to have a look at that. But what we just need to know is that we're going to set up our matrices so that we can solve it using that backslash operator. And that is also how it is then used in the DAP BC workbench. So another useful method for solving a set of linear algebraic equations is then called LU factorization. Over there, you basically break up your problem into, or your matrix into a lower and an upper matrix, and then solve it in that way. So it's some sort of a factorization of your matrix that you're doing, and this is then expressed in Appendix A of the PMD textbook. So this method is also useful in identifying any redundant equations, so in case the coefficient matrix A is singular. Okay, so then the kinematic position constraints, in contrast to the velocity and acceleration constraints on nonlinear algebraic equations. As it will be seen in section 12.1.2, nonlinear algebraic equations can be approximated as linear algebraic equations, and we can then solve that in an iterative manner for the unknowns. Okay, so then just going over to the next section, which is then the nonlinear algebraic equations. One frequently occurring problem in scientific work is to find the roots of one or a set of nonlinear algebraic equations of this form phi q equal to 0. So kinematic analysis of mechanical systems is one example for which the solution of position constraints in the form of equation 12.7 is required. As shown in PMD's example 5.2, the function fsolve in MATLAB can easily find the roots of such nonlinear functions for us. And then to learn how the zeros of nonlinear algebraic equations are determined, in this section we can discuss the common iterative process, which is the Newton-Raphson method. We describe this process first for one equation in one unknown, and then we can look at a set of n equations in n unknowns. And the fact that we have n equations and n unknowns also tells us that we expect a unique solution for our system. So for one equation, let's consider the following nonlinear equation in one unknown q. So phi q is equal to 0. Then the Newton-Raphson iteration for solving this single equation is given by algorithm NR1 over here. So we can assume an estimate for the solution qi equal to q0. We evaluate the function phi I equal to phi qi. And then if the magnitude of this phi qi is smaller than some tolerance parameter that we specify over here, then qi is the solution to phi q, and we can stop the iteration. Otherwise, we need to now iterate and we need to evaluate the derivative di, and this is simply the d phi over dq. We compute delta qi, and that is then given by phi I divided by di, and we improve the estimated solution using this qi plus delta qi, which is then qi plus 1. So in other words, we use the known quantities over here to iterate on this step, and this will then be returned to step 2 over here. Okay, so epsilon over here is then a small number that we accept as 0, so basically a tolerance that we specify on our solution. If the unknown q is an angle, regardless of whether we work in degrees or radians, the computed value for delta q will be in radians. And we must make sure not to add delta q in radians to q in degrees. So we can use the Newton-Raphson method over here to find the roots of this equation. For example, if x equal to x cubed minus 3x squared minus 10x plus 24. And over here, you can go and have a look at the solution. I'm not going to jump into this at the moment. We're not too interested in the actual numerical method applied over here. If you did have numerical methods in the first semester, some of these properties will look familiar to you. In our case, we're just interested in the actual iterative design process that is utilized within these simulations. Okay, so yes. So there are cases where it won't converge, yes. I think it depends on what iterative process you're using and what if your constraints that you specify are in line with the actual constraint rules that we specify when we do these drive constraints. I think we'll look at that in section 6 if I'm not mistaken. But over there, if your constraints are, for example, not correct or are not initialized and not connected correctly, then you're probably going to end up with a solution that is not going to converge. Or if you look at the animation in DAPBC, you're going to see that you're going to have these broken constraints. So certain mechanisms or bodies are going to move, others are going to be locked into place. Yeah. So the Newton-Raphson method, when it works, is very efficient, but it may converge to an unwanted solution if the initial estimate is not close to the desired solution. So in other words, it's it's sensitive to where we start with the initial design. It is also possible for the iterations to diverge. So this is what we just discussed. Therefore, it is essential to terminate the process after a finite number of iterations as well. And this is then done by specifying that epsilon tolerance over there. Yes.
I know if your marker matrix has an octave tendency, then it will just go away because of the gradient.
Yes. Yes, exactly. Yeah. So on a local level, we try to ensure convergence by specifying a reasonable epsilon value or tolerance. In the global sense, we just have to make sure that our constraints are well met. So if we can do those two things, then we expect a converging solution at the end of the day. Yeah. Okay, so then if we have a set of n equations, we can consider n nonlinear algebraic equations in n unknowns. And then the Newton-Raphson algorithm for n equations is the n-dimensional version of algorithm nr1. So you'll see over here, we just have these bolded out values over here. So that just indicates that we're working with a vector or a matrix. And then we are more interested in converging based on the norm of this phi I over here, which should still be smaller than or equal to some tolerance that we specify. So the array phi I is then known as the array of residuals, which corresponds to the violation in the equations of the constraint. And the term norm, phi I, which is smaller than or equal to epsilon, is then the norm of the residuals that we take into account. So if this term is smaller than the specified tolerance epsilon, then every residual is small enough to stop the iteration, and we can consider the solution to be converged. Okay, so then I think this wraps up the nonlinear algebraic equations, and also then the kinematic relations that we wanted to look at. So at the moment, we haven't really considered any dynamic properties. We haven't really looked at how the mass matrix, well, we did actually look at the Jacobian matrix, how that can have an effect on the kinematic analysis. But now instead, we want to jump over to section 12.2, which then so the equations of motion for a mechanical system represent the relationship between the forces that act on the system and its motion, which we obtained from the kinematic analysis. Inverse dynamic analysis of a multi-body system requires a kinematic analysis to be performed first, so that we can define these coordinates, the velocities, and the accelerations. And once we have this available, then we can go and evaluate the forces. So if Q does not contain the complete kinematics of all the bodies in a system, in the case of a vectorial formulation, for example, the body coordinate arrays of C dot and C double dot must be determined prior to performing a force analysis. Now the equations of motion for a system based on either the body coordinates from equation 755 or the free body diagram method can be formed using this equation over here, and this is something that we looked at, I think, under section 4 as well. So we have MC double dot, M being our mass matrix, and then we have C double dot, which is our acceleration vector, which is then equal to HA. So this denotes our applied forces, and then we also have these Lagrange multipliers over here, which relates to the reaction forces. And we just multiply that with D prime, which is our Jacobian matrix. And in addition to this, since we now have driver constraints, we also have to specify this term over here. And in that case, we just consider the Jacobian matrix for the driver constraints multiplied by this lambda of the driver constraints as well. So the driver reaction forces, basically. Okay, so the Jacobian matrix and Lagrange multipliers associated with the driver constraints are included, but we separate those from the kinematic joints. For our driven pendulum rod, it follows that we have our mass matrix denoted over here. So it's a diagonal matrix over here with M1 in the first two rows. And then we have J1 in the last row, which is just to relate the moment equilibrium as well. And we can expand this, since our only applied force in this case is weight. We're just going to denote that in the Y direction. Then we plus this Jacobian matrix that we have over here, which we then want to multiply by the reaction forces for the kinematic joint. In our case, we're working with the revolute joint. So lambda 1 and lambda 2 are then the reaction forces in the x and y directions. And then we can simply plus this Jacobian matrix for the driver constraints, and we multiply that with lambda 3. So since we're applying some sort of a rotation driver over there, we expect to get a torque out, so we just want to place that in the last row, which deals with the torques. Okay. These equations can then be rearranged in this form, so we can combine both the Jacobian matrix and then the driver Jacobian matrix over here in a single matrix. And then we multiply that with our Lagrange multiplier vector over here. So over here we also combine the kinematic joint Lagrange multipliers with those of the driver constraints multipliers. And that is then equal to MC double dot minus HA. So we just take that HA over so that we can calculate the applied forces on the right hand side. So for our driven pendulum rod, equation 12.11 can then be written in this form over here. So now we've combined the Jacobian matrices. We've combined our reaction forces or our reaction moments over here. And then we just, on the right-hand side, have our known quantities as well. Since the coordinates, velocities, and accelerations are now known, the coefficient matrix and all the terms on the right-hand side can numerically be evaluated. Then the equations are solved as a set of linear algebraic equations for the Lagrange multipliers. So in other words, once we have everything on the right-hand side and we want to solve these Lagrange multipliers, we also know on the left-hand side, we know our Jacobian matrix, so we can simply use the backslash operator to go and calculate our lambdas. So the results for d prime lambda provide the joint reaction forces and torques, and that of d prime driver lambda driver yields the forces or torques associated with the driver motors. For our driven pendulum rod, the joint reaction forces and torques are thus given by these equations that we have over here. I just want to check, I see they okay, so they only have lambda 1 and lambda 2 over here. But in our case, we can actually go and find the lambda 3 as well, because we know all of these properties that we got from our kinematic analysis, and we also know these properties. We know what the mass is, we know the accelerations, and we also know this mass moment of inertia over here. Okay, so for the driven pendulum rod, the torque associated with the driver motor is then given by this 0, 0 lambda 3 that we have over here, and we can simply denote that as lambda 3. Okay, right, any questions on this so far? All right. Okay, so then I think the last point that they just illustrate over here is then the overall algorithm that we want to use. And this is then also something that we apply in the body coordinate formulation, or the DAP-BC program. So in this case, we first construct the mass matrix and the array of applied forces. We then construct the Jacobian matrix for the kinematic joints. We can also construct the Jacobian matrix for any driver constraints that we specify. And finally, we can solve this equation 12.11 for the Lagrange multipliers. And those will then be our reaction and our driver forces that we have over there. Okay, so I think that then wraps up the inverse dynamic analysis. Yeah, so that is then everything that we wanted to look at for section 5, which is then for a driven pendulum rod. Okay, so now we can finally get to, I think, the fun part of the module. So that is then looking at the actual DAP-BC workbench and how we can go and apply this pendulum rod to solve for either reaction forces or some sort of a kinematic relations that we want to look at. Okay, so to perhaps first start off with where you can find the workbench. So if you head to ClickUp, you'll see there's this DAP-BC workbench material section over here. And yesterday I uploaded the recent version, so that's DAP BC 12 2022. Previously it was DAP BC 11. So if you go to planar multi-body dynamics, if you search that and you go to, I think it's Root-Ledge, then you'll see the workbench that is available over there is DAP BC 11. So DAP BC 12 has a few additional functionalities as well. We can also now define some more complex functions once we want to go and look at those driver functions. And yeah, so overall the stability of this DAP BC 12 is overall a bit better. So we're instead going to use BC 12 to solve our problems. So once you have this open, you can just click on the link. It will download the zip file. You can just unzip it. And then you can head over to Octave, or if you want to, you can also use MATLAB. In our case, we're just going to use Octave. It tends to be a bit faster than the MATLAB versions. So I'm just going to open up Octave over here. And then you can just go and move to your relevant folder where you save this document. So I'm just going to go to, in my case, document. And then we have the DAP BC 12 that we're working with. So if I open up this one, you'll see it has this formulation, models, anim, DAP, post files in over here. So I don't want to go into one of these folders. I instead want to work in this global folder. So I'm just going to click on choose then. Okay, and then it opens up these this folder over here that we're going to work in. And then usually before we start doing a new analysis, what I like to do is just to make sure that I clear all the variables, so that I'm basically working with a blank canvas. And I think maybe what I should also do is just increase the font a bit. Let's see, I think we can maybe make it, let's see if we make it 14. Okay, so then we can just type in over here, first clear all, so that makes sure that there aren't any variables stored in your current version of Octave or your current run that you're performing in Octave. Then you can also say close all, so that just makes sure that if there are any figures that are open, it will then close those figures. And then finally, we can also say CLC, so that will just clear this command window as well. Then I can hit enter. Okay, so before we now jump in, let's quickly look at the undriven pendulum rod's kinetics. And my advice would always be to first start off just with a regular diagram of where you want to locate your local coordinate system and then your global coordinate system as well. So your local coordinate system for the DAP BC workbench will always be located at the center of mass. So in this case, we can assume that the center of mass is at the center of this rod, so at the geometric center as well. And I place it with xi in the direction of the rod's longitudinal axis, and then eta will just be perpendicular to that. So we are working with a right-handed coordinate system as well. So if I define xi in this direction, eta needs to face upward. Then for the global coordinate system, this is really up to you where you want to define it. It's in this case better to perhaps define it at the revolute joint. You'll see that it's going to refine some of the equations that we want to write out. But if you, for example, wanted to place it, let's say over here in this corner or at the top right, you could do that as well.
Assuming we have to determine the center of mass for like
yes.
irregular geometry.
Yes, that's correct. Yeah, so we're going to need that in our first input file that we're going to look at, or the second input file rather. So we need to give the actual coordinates of the center of mass. So you'll need to determine that. Yes. Okay, so then with this in place, we now know from the information that was also given in the mind map that the length of the pendulum rod was 0.6. So we can just break that up into 0.3 meters. And then I think they also gave us the angle over here, which was 30 degrees, if I'm not mistaken. Okay, so then we just want to perform some initial or preliminary calculations as well that we can later on use for sanity checks. So in this case, I decided to place the psi eta coordinate system over here. I could have also placed it at the center of mass. It doesn't really matter for this initial calculation that I'm going to do. I just want to relate the forces that I calculate over here to the X and Y components. Once I have that in place, then I can use that to check the reaction forces that I'm going to get at the end. Okay, so it would be totally fine if you wanted to place psi eta over here as well as we had with the original schematic. Then the information that is given over here, so theta is equal to 60 degrees with respect to the vertical. Then we have the mass, which is 2 kilograms, and the length 0.6 meters. Okay, so in this case, it's the undriven pendulum rod. So the only force that is going to act on this system is then weight. So this is this mg that I'm denoting at the center of mass. And then I can go and break it up into its two components. So mg sine theta, mg cosine theta, which are then aligned with the psi eta directions as well. Okay, so then I can go and apply the moment equilibrium around point A. I choose to do it at about point A since I don't actually know what the reaction forces are over here. So if I apply the moment over there, those reaction forces won't have an effect on the moment calculation, and it makes it a bit easier to then perform this calculation as well. So what I'm just going to say is sigma m about point A is equal to IA theta double dot. And what I want to calculate over here is then this rotational acceleration. In this case, since I'm applying the moment about point A, I also need the mass moment of inertia about point A. So depending on where you apply your moment equilibrium, you need to use that specified mass moment of inertia. So if we look back at just a few general formulas for the mass moment of inertia, you'll see that we have the calculation of that moment of inertia about the center, and then we also have it about the end. In our case, we're then going to use the moment of inertia about the rod end, so that will be this 1 over 3 ml squared. So if I then go back to my calculation, you'll see that IA, I just substituted that in, a third ml squared times theta double dot. And on the left-hand side, I then do my moment equilibrium, so that will simply be this force that I have over here. So mg sine theta multiplied by L over 2. And if I look at the direction, it's going to cause a clockwise moment. So in other words, it's negative, since we assume counterclockwise is positive. So if I then go and rearrange these terms, what I end up with is theta double dot is then this equation over here, and that is then minus 21.24 radians per second squared. Okay, so now I have this theta double dot. Now I can go and also calculate firstly this force over here. So sigma F around the xi direction, and this is the xi direction that I denoted over here. So if I look at the forces over there, I expect to have some reaction force that I can assume is going to sit in line with this xi direction over here, minus mg sine theta. And that is then what I did over here. So this is the reaction force in xi. And I set that equal to ml over 2 theta double dot. So this is just based on the two components that you have for your acceleration. In our case, since we're working with the xi direction, we're interested in the tangential acceleration. And the function for that is the acceleration is simply equal to r times alpha. So that's just what we're applying over here. So r in this case is as theta. Okay, so if I rearrange these things, since I now know what theta double dot is, I can go and find in psi over here. I think we actually did two different equations over here, but you could also always just find it directly from this force equilibrium over here. And then I can also go and apply the moment equilibrium about point B. So point B is then the center of mass. So in that case, I'm just going to use the center of mass moment of inertia. So that's the 1 over 12 ml squared that we have over there. And if I solve that problem, then in xi is given as -1/6 ml theta double dot. Now, if I substitute 3 into 1, then I can end up with this function over here. And once again, I can go and solve for, if I just move this out of the way, I can go and solve for theta double dot. And you'll see this matches what I originally got at my moment equilibrium for A. Right, so then I just go and solve in xi with whatever force equilibrium I want to use. So that's then 4.25 newtons. And then I can do the same for in eta. So this is then the reaction force in the eta direction. And if I look at this one in eta, we can assume is facing upwards. And there's only going to be one force to counteract that, and that is this component of the weight, mg cosine theta. And then its acceleration is going to be r times r omega squared. But we know that we're starting from rest as well. So in other words, the theta dot is going to be 0 in that case. So when we calculate in eta, it will simply be equated to mg cosine theta, and that gives us 9.81 newtons. And then finally, I can also go and relate these forces that I now calculated in the local coordinate system to the xy coordinate system. And then I use these two equations. These are fairly standard equations that I can use for that. And then what I end up with is that in x, or the reaction force in the x direction, is -6.37 Newton. And then in the y direction, it's 8.58 newtons. So this is only for the initial condition, or the starting point. However, once I generate my points for whatever time step or time interval I want to use, I can always go and check whether the first time iteration is in line with what I got over here. So just basically a sanity check that I want to do at the start. Okay, so now it's simply carrying over this to the DAB-BC workbench. So what I'm going to do is on the left-hand side where it shows the folders, I'm first going to head to models, and I just want to expand it. I don't want to double click on it, otherwise I'm going to work in the local folder. I instead want to remain in the global folder. It just makes it a bit easier to then navigate between the output files as well. Okay, and then I have this PRB over here. So this is the pendulum rod that is undriven. And I'm just going to open up all of the input files so then we can head through that. Okay, so first input file that you should see is the inanimate input folder or file over here. So for this one, we can specify any points that we want to use for animation purposes. So in other words, the point doesn't actually, it's not really used for any, let's say, joint purposes. So if you have a revolute joint, you would specify those points under in points. But if I just want a point to visualize the motion, then I can specify it in this inanimate file over here. So you can leave it blank if there aren't any points that you want to specify over here. However, it is important over here that we specify the variables for the 3D animation axes. So in other words, the limits of our axes. In this case, we chose x min as -1, x max as 1, y min as -1, and then y max as 0.2. So if we go back to our original diagram that we have over here, the reason why we chose that is if we look at this revolute joint, which is located at the global coordinate system or the global coordinate axis, then if I have it horizontally, the maximum reach of this pendulum rod is 0.6 meters. So if I decide to instead make that limit, let's say 1 meters, I should have a large enough window to actually simulate and animate what's going to happen with this pendulum rod. So that's why I use -1 and 1. And then of course, since it is an undriven pendulum rod, I don't expect it to actually go higher than whatever its initial angle over here is. So if I perhaps use 0.2 over here, that will also be fine. It won't ever reach 0.2. It will always basically oscillate here at the bottom. Okay, so that's simply the choice that I made over there. Then The next important file is the inbodies.m file. And over here now I start to define the actual bodies that I'm working with. So in my case, I have a pendulum rod which consists of a single body. So what I'm going to start off with is this B1 equal to body underscore struct. So this remains as it is. This basically initializes the body as a body structure. And this structure is then going to have a bunch of characteristics that I have to specify as well. So once I've done that, then the first characteristic that I want to define is the mass of the body. So that will then be B1.m, and we know that that is 2 kilograms, so I'm just going to state it as 2.0. I think you could have also just said 2. You don't have to put the 0.0 over there, but it just makes it easier once you've to instead from the get-go convert to float instead of working with integers. Okay, then the next one is B1.j. So this is then the mass moment of inertia, and this is always at the center of mass. So in our case, it will be 1 over 12 ml squared. We just calculated that value initially, and that gave us 0.06 kilogram meter squared. So I just put in the actual value over here. But you could have also said 1 over 12 times B1.m times 0.6 squared. Okay, so once we have these mass properties in, then the next thing is to initialize our center of mass location. So that is then B1.r. And I set that equal to whatever these values over here are. So what I do is I use a list to specify them. And then I also separate firstly my x values from my y values with a semicolon. So to find this point, we can either do it trigonometrically. So if I go to this one, we know this is 0.3. We know the starting angle with respect to horizontal is 30 degrees. So I can actually go and calculate what the center of mass is over here. Otherwise, you can always use something like FreeCAD or SolidWorks. Just create a simple little schematic and actually go and measure where that center of mass is. Yes. Yeah, so that's with respect to the global coordinate system. So in this case, everything that we're going to specify is with respect to the global coordinate system, and our mass moments of inertia will be at the center of mass of each of those bodies. Yeah. Right, so once I have that in place, then I also need to give the starting angle for each body. So in our case, we know that B1.p, so our starting angle is minus pi over 6, so this is minus 30 degrees. If I go back to the schematic that I have over here, you'll see once again it's with respect to the global coordinate system. Since it's below the x-axis, I'm going to use minus 30 degrees. You could have also taken it from the horizontal axis, so then it would have been 360 minus 30, so 330 degrees that you could specify over there. In our case, it's maybe just a bit easier to visualize and to understand if we make it a negative angle over here. Okay, so then lastly, we also have B1.r underscore d, and this is then an optional argument that we have to give. If we do not know the starting velocity, we can always do some initial condition correction. We're going to look at that once we run the program. But in this case, we know that it actually starts from rest, so we can just say 0, 0 over there. If we don't put any value in over here and we don't initialize it, then we don't do any initial condition correction, then it's going to take the default value, which is in any case 0, 0. So once we've done all of that for our bodies, then we just need to create this list over here where we combine all of the bodies. So this would be B1 in our case. If we had a body 2, then we would just separate them with a semicolon. So then it would be something like semicolon body 2 and so forth for all of the bodies. Yes.
So one of the examples you once demonstrated, which was the linked pendulum.
Yes.
Would that be 2 bodies? Or
yes. Yeah, so that would be 2 different bodies. Reason being the 2 pendulum rods are connected via a revolute joint. So we model them as 2 different bodies, and then we connect them under the in joints file that we're going to look at. Yeah. Yes.
So is that just your initial velocity that you specify?
Yes, that's correct.
Do you specify it by specify XY coordinates, like I, or radial coordinates?
It will also be in the global coordinate system, so XY coordinates, yes. Yeah.
Let's say if you have your starting angle at 0, then you're going to specify a y velocity in negative direction.
Yes. Yes, that's correct. Yeah. Cool. Yeah, so if you are interested, I think, in the relative velocity, then it would be, so it depends if you're working in which body you're working, but since we're working with rigid body kinematics, we instead just specify the global velocity, and then the system will be able to calculate the location and the velocity and all of those things for the points on that body. Yeah. Okay, so once that is done, then we can head over to our third input file, and this is then the inforces.m file. In our case, we know that there's just a single force that we can consider. So we're first just going to initialize it as a force structure. So we just say S1 is equal to force underscore struct. It doesn't really matter what you use for this S1 over here. If you want to call it, let's say F1 or D1 or something like that, it's also fine. As long as you just initialize it as a force structure. And then once that is done, you can say S1.type. And in our case, we're working with a weight. So we're just going to specify over here weight. You'll see under, if we perhaps quickly go to the appendix, I think it might be easier to just access it from ClickUp. Okay, so you'll see you have this tab BC user manual over here. So if I just open this in a new file, it also gives a breakdown of all the different types of forces that you can put in. If we scroll down a bit, yeah, so over here we have the force structures that we can use. So in our case, yeah, so we can either have something like a point-to-point force. I think there is also a rotational SDA, which is a spring damper actuator that we can specify. If local, which is then a constant force that we describe in the body fixed frame, so in the local coordinate system. Otherwise, we can also apply a constant force in the XY frame, so that will then be denoted as F. We can also specify a constant torque T, and any user supplied forces can then be given as this user over here. And then we have to also create a user force.m file, but we'll look at that in a later application example. Okay, so, but in our case, this is satisfactory, so we can just specify our force as a weight, and then once again, we just place this in a list at the end. So forces equal to S1. Right, so then next up, we have this infunct.m file, and this is where we're then going to specify any functions for driver constraints that we have. So remember, for this example, we're considering an undriven pendulum rod, so we don't have any functions that we want to specify, so we can just leave this funct equal to as an open list over here, or an empty list. So then we can also head to in-joints. And before I actually look at in-joints, I think we should have a look at in-points first, since the in-joints file depends on the points that we specify. So in my case, I specified 3 different points. You could have also gotten away with just specifying 2 different points. Point 3 is simply for visualization purposes. So if you perhaps wanted to place this under inanimate, that would have also been fine. But what I need to do is, if I go back to my schematic over here, you'll see that I have a point 1, 2 over here. So whenever I have something like a revolute joint, I need to have a point on both bodies that are then going to join each other once I specify that kinematic joint under the injoints.m file. So I specify point 1 on body 0. So body 0 is ground. So it's this grounded revolute joint that I have over here. And then point 2, I can go and specify on the actual pendulum rod, which is then body 1. So it's also just important to note that for in bodies, we don't specify ground as a body. It's already taken into account once it does these calculations. So we just want to specify the actual bodies that are going to move that are not fixed into place, if you will. Okay, so in our case, point 1 is then initialized as a point structure. Then we have p1.body index. So this specifies on which body this point lies. In our case, it's 0, so it's the grounded point that we have over here at the revolute joint. And then it also asks p1.sp local. So whenever we have a point on ground, it means that we have to use the xy coordinate system to basically fix the points into place. So since we made the deliberate decision to place the xy or the global reference frame at the revolute joint, we know that its location on ground will be 0, 0. Okay. Then for point 2, this is now the point that we want to specify on the pendulum rod. So once again, I initialize it as a point structure, and now p2.body index or b index is then equal to 1. So now I refer to body 1, which is the actual rod. And then I just have to place that point with respect to its local coordinates. So that's why I say p2.sp local. And that is then equal to minus 0.30. Reason for that being, if I go back to the schematic, here I have my local coordinate axis. So in other words, point 2, which is located on this body, is in the negative xi direction. So it's minus 0.3, and it's in line with this longitudinal axis that I have over here. So it's 0 eta. Okay, so then that point is specified. Then I can also just go and specify point 3. So initialize it as a point structure, define the body as being body 1, and then its local coordinates will just be on the other side. So this point over here. And since that is then in the positive xi direction, it's going to be 0.30. Yes. Yes, so that's basically a property of your structure that you created for point struct. Yeah. So these are basically the only characteristics or the only properties that you have to specify for a point structure. Once those two are defined, then you have a fully defined point. Yeah. Once that is then done, we can then just place all of our points once again in a list. I separate them with a semicolon. So now that I have all of these points specified, now I need to actually go and define the joints. Yes. Yes. Okay. Yeah. Yeah. So it's overall it's actually easier to just specify it from the local coordinate system, and then the system or the body coordinate formulation is in any case going to calculate the global coordinate systems location. Yes.
Which for X and Y is the local coordinate system for your
Ground.
Anyway.
Yes, that's correct. Yeah. Okay, so then moving over to the in joints file, if we just quickly look back at our schematic again, we now know that there's a revolute joint over here at the global coordinate system's origin. So this is the joint that we then want to go and specify. So to do that, I once again start off by just initializing a joint structure. So that will be J1 equal to joint underscore struct. Then I need to specify what type of joint I'm working with, what type of kinematic joint I have. And in our case, it's a revolute joint. If you once again go to this file over here, the appendix B, I think they do have in joints available as well. Yeah, so over here they give a breakdown of the different types of joints that you can specify. In our case, we want a revolute joint. So we just specify rev. If we want a translational or a sliding joint, so this might be something like a slider crank mechanism where you have a piston or a sliding block that is translating left or right, then you're going to specify a translational joint. A revolute joint or a revolute joint is then rev-rev. And then revolute translational joints. So these are basically combinations of the separate types of joints that we have. A rigid or a bracket joint can also be specified. A rolling disc, which would be something like a wheel that you want to specify, that will be a disc. And then we have these last two, which is a relative rotational driver, so that we specify as rel dash rot, and then relative translational driver is rel dash tran as well. So these last, we're probably going to have to specify some sort of a function when we define them. Okay, and over here you can also see there's a list of input arguments that you have to give for these different points or these joint structures. Okay, so in our case, since we're working with a revolute joint, we just need to specify the 2 points that we're working with. So what is the point on the one body? What is the point on the other body? So if I go back to this file, once I specify the type as rev, then I can say j1.ip index is equal to 1. And what I mean by that is the first point that I have over here on body 0, so that is the grounded revolute point. And then since the joint exists between the 2 points on the pendulum rod and the grounded revolute joint, then I can say point 1, point 2 are the 2 point indices that I have, so 1 and 2. So I just extract, these are the indices in the list that I have to extract. So P1 is index 1 and P2 is index 2. Okay, so once that is done, I just combine everything in this joint list over here at the end. And lastly, I can just go over to in U vectors. In our case, this U vectors is an empty list. Reason being, we don't really have any translational joints that we want to specify at this stage. So U vectors is usually applied only to translational joints when you want to create either opposite or parallel motion between 2 bodies. Right, so once all of that is done, then I'm ready to actually run the program. So what I'm going to do, and you'll see if you're working in the global folder over here, you'll see you have this dap.m file over here. So what I'm going to do is I'm just going to type in dap, and then it asks me a question, which folder contains the model. So the folder in question over here is this pr_b, and this is because all of our input files are summarized under this folder. So I'm just going to type in over here pr_b. Then it asks, do I want to correct the initial conditions? And I can choose either yes or no. Usually it's best practice to correct these initial conditions, mainly to ensure that there is continuity between the bodies once these problems are being solved. So once you start working with 3, 4, 5 bodies, you might have some constraint redundancies. The initial condition correction will therefore eliminate these redundancies and make sure that all of the bodies are correctly connected. So in my case, I'm just going to say yes or Y. And then we can see over here, it then gives us the corrected coordinates. So these are the coordinates of the center of mass of the bodies. So we can see X and Y are what we specified originally, and then phi, which is the degrees, is also -30. We just specified it in radians as -π/6. And then X dot, Y dot, and phi dot are also given as 0, 0, and 0. So that is also correct since we're starting from rest. Okay, so then I can also go and specify the final time. So that's the next question. So let's say I want to simulate this for 3 seconds. Then I can just type in 3. And then the reporting time step, I can make, let's say, 0.01, so fairly small. Okay, so, and then if I hit enter, yes. Yes. So that would be the times at which it prints out the results. Yeah. So if you, I think if you look at well, actually the next lecture that we're going to do, we're going to look at integration time steps as well. So if you use something like a Runge-Kutta integration method, that integration time step differs from this reporting time step. So this is only the time steps at what it has to give out information to you. Yeah. Okay, so once we pressed enter, we can now see that it basically gave us a bunch of values over here, and then the number of function evaluations that it performed as well. And the fact that it then gave this number of function evaluations at the end means that everything converged, and we expect to have a reasonable solution over here. Right, so now I can do one of two things. I can first go and look or I can first go and look at the actual animation, or I can run the post-processor. And the post-processor then just wraps up all of the outputs, so it gives you the reaction forces that you can then go and plot the location of the body at each time step as well. So let's perhaps first just look at the animation. So I'm just then going to type in anim, and I'm going to hit enter. So then it gives me this graph that I have over here. And what I can see is that the -1 x limits that I use seem to be sufficient. So I expect that the maximum over here is 0.6. And then on this side, -0.6 as well. I don't expect it to actually go above the horizontal line over here. Okay, so if I'm not going to close it, but I'm just going to keep it open, and I'm just going to click back on this command window over here, and then you'll see it says press any key to continue. So if I press key, then you'll see it starts to move. Right, so now we can see the actual oscillating motion of the system. And as expected, we don't really expect this system to go beyond whatever the initial angle was. Since we also don't have any resistive forces like any wind resistance or any dissipative forces over here, we expect that it will always oscillate between -30 degrees up to whatever the other angle is on the other side. So yeah.
Is there any way to specify those resistances?
Yes, so depending on what type of force you would like to specify, you can do something like maybe a spring mass damper system, or specify a damper, any of those things. Or if you want to specify a resistive force, something like let's say an aerodynamic force or something like that. Yeah, so friction as well, you can actually specify that as a user force. So that will be something that we're going to look at one of the later example problems. But it does allow you to specify a force if it's not one of the standard forces that are given in the document. Okay, so I just want to wait for this one to finish, then we can actually go and look at the post-processing data. Okay, here we go. So now it's stopped, so now we can actually go and close this. And now we can go and look at the actual data that we get out. So I'm just going to type in post, hit enter. And now over here on the left-hand side, some of the variables that I have available has now updated. The ones that I am perhaps more interested in would be this lamb over here. So this is the Lagrange multipliers. And you'll remember for the revolute joint that we specified, we expect to get 2 Lagrange multipliers out. One for the X reaction forces, one for the Y reaction forces. So if I go to this lamb over here and I just double click on it, it opens it in this spreadsheet that I have available over here. And you will see if you scroll down all the way that I now have 301 points over here. And this is simply due to the reporting time step and the time step size that I specified. So since I have 0.01 time steps, or a time step of 0.01 seconds up to 3 seconds, I expect to get about 300 points out. So that's fine. So another thing that I can then go and check out is at the very first time step that I have over here. This is where it's initialized. And I did some calculations to check what these forces will be initially. So just to do a quick sanity check, we can go back and we see that Nx was originally -6.37 and Ny was 8.58 newtons. If I go back over here, I can see that now it's 6.37 newtons and -8.58 newtons. The reason why I get a different sign over here is simply due to the basically Newton's third law on the reaction forces. So I perhaps calculated it originally on the pendulum rod, where this system then calculates it on the grounded revolute joint. But the sign itself doesn't really matter as long as the magnitude is correct to some extent. Yes, that's correct. Yeah. So the fact that I get the correct magnitudes over here gives me confidence that this is actually the correct problem that I want to solve. Okay, so I can then close this one, and then if I perhaps want to look at the position of these points as well, or the position or location of the center of mass of body 1, I can scroll down, and over here I see this R variable that I have over here. So if I double click on this one, then it opens up this list of values or array of values. So first it's going to give me all of the X values. We can see it does start at 0.2598 as initially specified. And then if I go down, it will then give me the Y coordinates after that. So that will then be minus 0.15 that it starts off with as well. And then under that, I also have RD, RDD. So these are just the velocities and accelerations as well. And if I'm perhaps interested in, let's say, these orientation angles, then I have P. So P will also just be a spreadsheet with all of the angles in radians. And then I have PD and PDD, which are the rotational velocities and rotational accelerations. Okay, so now I can go and plot some of these values. So let's perhaps create a new script. So what I'm just going to do in the command window is type edit, and then I can hit enter. So then it will open up a new script over here that I can go and save. So let's maybe save this one, and I'm just going to call it post_plot.m, and then I can hit save. Okay, so now I can go and plot some of these functions. So let's perhaps first plot, let's say the position of, the center of mass. Okay, so if you are familiar with Python and its matplotlib functionality, the MATLAB and Octave functionality is more or less the same. It's actually a bit simplified. So if you understand the whole import matplotlib thing and how to create plots over there, you can also do similar functions over here. So I'm perhaps just first going to start by saying figure 1. So I just want to initialize my figure. And now I just want to go and create a plot. So I'm just going to say plot. And we want to get the center of mass in the X and Y. We want to compare them to one another. So I'm just going to say R. Then if I type in a colon over here, it means it's going to get all of the time step values. But if I look at R over here, I can see it's a 301 by 1 by 2 matrix that I have. So the 301 is the time step, so that's fine, that's what I want. 1 denotes the body that I'm working with. So since I only have one body, I only have one column over here basically. And then by 2, so 2 is simply to say that I have X and Y coordinates stored in this matrix. So I'm just going to say R colon, and I'm going to type in 1 and comma 1 as well. So then I have my X components on the X axis, so that's fine. Then I'm just going to place a comma, and I'm going to say R, more or less the same, so it's just going to be colon for body 1 in the 2 direction. And let's say I want to denote these points by black dots. So then I can just type in K dot over there. Okay, once that is done, I can just add a semicolon over there. And I'm not going to place in a legend or anything. But what I do want to do is perhaps place in a title. So I'm just going to say the position of the pendulum rods. Just say center of mass, something like this. Okay, and then I can just add X label as well. So X label will just be the X point, which is in meters, and a Y label as well, which will then be Y in meters. Okay, and then perhaps I want to show the grid as well. So I'm just going to say grid on. And just to make it a bit easier to visualize, I can also say axis equal. Okay, so once I've done all of that, I can just go and run this one. So I'm just going to say over here post plot. Okay, and this is then the plot that I'm going to get for the center of mass. And we can see that it does start over here at minus 0.25, or sorry, 0.2598. If I look at the bottom over here, I can see those coordinates match. And we can see it's some sort of an oscillating motion that I have over here. The points are a bit more dense over here at the edges, and that is simply because of the acceleration, the acceleration and deceleration over here as it's moving and reaching a maximum velocity here at the bottom. The fact that I also have these points that are then spaced fairly close to one another, these 4 points, that is simply due to the time step that I use. So for each oscillation, it maybe generates a point just to the left or just to the right of the previous point. But overall, I can see that the motion is in line with what I expect over here. Okay, so perhaps if I want to go and check what the relationship is with respect to time for each of these things, then I can go and create a new figure. So I'm just going to say figure 2. And since I want to perhaps create more than one plot now for, let's say, the x, the center of mass x point as a function of time, then for the y points as a function of time, and then perhaps also for the orientation angle as a function of time, what I can create is firstly handles. So I'm just going to say in this case h1 is plot, and I'm going to use time, and let's say r. So now I just want to plot the x components, and let's maybe make that a red line. Then I'm just going to say hold on. So that just makes sure that it doesn't plot this first function and then overwrites it with the second function that I want to plot. So then I'm just going to create my second handle, h2 equal to plot, t, and it will be r, all of the points, or all of the time steps for body 1 in the 2 direction. And let's say I want to use a blue line to denote that. Once that is done, I can just say specify perhaps a legend to make it a bit easier. So legend in brackets, I'm going to say h1, h2, comma, and then I can say x points, y points, and then I can also perhaps specify the location over here, and let's say it's east outside. So just to place the legend outside of the actual graph. So once that is done, then I can just add perhaps an x label as well. I'm just going to call this time in seconds. Y label we can make, say, position in meters. So I'm just going to say position meters. Okay, so I'm not going to add a title now, but I'm just going to say grid on here as well. Okay, and then if I go back and I run postplot again, then it now generated figure 2 over here. And now we can go and see how the position changes for x. We can see it is indeed oscillating with respect to time, and the y points are also oscillating with respect to time. And we don't see a decrease in the magnitude or the amplitude of these oscillations because we don't have any resistive forces. So this is what we expect to see as well. Okay, so maybe I can also go and plot, let's say, the reaction forces that I now got out. So I'm just going to say figure 3 now. And in this case, I perhaps want to show the reaction forces in the x direction, in the y direction, and then also the resultant reaction force. So I'm just going to create a new handle, G1, and I'm going to say that is equal to plot. And what we can say is with respect to time. And now I just have to go and call Lagrange multipliers correctly. So I'm going to use the lam variable over here, and if I look at the form that it has, it's a 301 by 2 matrix. So the first column will contain the x values, the second column will contain the y values. So let's first plot the x values. So I'm just going to say lam all of the time points in the x direction, And let's do a red line for that one. Then I'm going to say hold on again. Then I can specify G2, which is plot time versus the Lagrange multipliers, all of the time points in the 2 direction. And let's use a blue line for that one. And now I can go and specify G3 as well, which is then the resultant force. So that will be equal to plot time. And now I just have to specify basically Pythagoras to calculate the resultant force. So that will be Lagrange multiplier. Let's do that in the 1 direction. I'm just going to place dot squared. So this makes sure that it squares it on element-wise basis. And then I can say plus Lagrange multiplier, all of the time points for the x points over the, or the y points over there, square that one as well. And then I just have to remember to add square roots at the start as well. Okay, and then I can use perhaps a black line to denote that. And I'm just going to say hold off. And we can say grid on as well. So if you want to add a legend or something, you can do that at the end as well. In my case, I'm now just going to rerun postplot. And if we now look at the forces, we can see that the X reaction forces are these forces over here. So it's also more or less oscillating. It just seems to make 2 prominent peaks before it moves over to the next period. And then for the Y components, we also have this oscillating force, so that's fine. And then the resultant force over here at the top is also oscillating, so that's also correct.
What might be the cause of the?
I think it's mainly just because of the actual trigonometry of the system. So Y doesn't give you that those 2 prominent peaks, because it's in the Y direction that you have that motion of it swinging. The X direction is maybe calculated a bit differently, so I think it might be a combination of two trigonometric functions that you basically amplify with one another, so sine and cosine. Yeah. Right. Okay, so if we perhaps want to, we can also go and plot. Let's say I'm just going to copy over figure 3, and we can maybe go and look at the velocities as well. So I'm just going to call it then figure 4, and maybe change this to F1, F2, F3. So F1 can then be, once again, with respect to time, but now I want to go and create the velocity point. So I'm just going to say RD. Go and look at what RD denotes. So over here it's a 301 by 1 by 2, so the same as what we had for R. So in this case, I'm just going to say for all of the points for body 1 in the 1 direction. Then for the second one, I'm just going to copy over RD over here. And that will then be in the 2 direction, so that I can see what the Y velocities look like. And then a combination of these 2 will give me the speed of the system. So I'm just going to replace this one over here with RD11, and RD12 will be over here. Okay. And then if I go and run postplot again, right, so then I can see that this is my functions that I get over here for the velocity. So I have my velocity in the X direction, velocity in the Y direction, and then since I'm calculating the magnitude, I'm getting the speeds out over here. And this also seems to be oscillating, which is also correct. Okay, so those are some of the things that we can actually plot. Yeah, so you're more than welcome to also go and have a look at some of the other components. So for example, RDD, if you plot the accelerations, how is that one going to look? If you want to look at the angles as well, we can maybe do that as well. Let's just head over here. And I'm not going to add too many too many labels and stuff, so I'm just going to call it figure 5. I'm going to create a plot of time versus the orientation angles. So the orientation angles is a 301 by 1 matrix. So that will be all of the time steps for body 1 that I want to go and plot. And then I can use perhaps a black line for that one. And I can say grid on, and save that one, and I can also run postplot just from this play button over here. And if we look at that, we can now see the oscillations in the angles as well, okay, which is also as expected. We don't have any decrease in the amplitudes because we don't have any dissipative forces. So this also matches what we expect to get out. Okay, so yeah, you're more than welcome to go and check the other accelerations, the velocities as well, how you want to plot those kind of things. Any other questions? We move on. Okay. Okay, so then we can now go and look at the driven pendulum rod, and I think for today I'm just going to focus on the initial calculation that we have to do, just to do our sanity checks at the end. So if I then head back to the DAP-BC workbench, so you'll see if you go into the DAP-BC12 file and you go to models, under PR_B, I've given this undriven pendulum rod information over here, that's these calculations that we performed over here. So I did the same then for PR_D, so this is then the driven pendulum rod. And this one is then just called driven pendulum rod kinematics. I also have this pendulum rod over here, but you'll see it looks exactly the same as what we had for the undriven pendulum rod. So it's just a schematic that we're going to use for reference. So in our case, we're interested in the driven pendulum rod kinetics. So I'm just going to open this one. Okay, and this is now what our free body diagram is going to look like for the rod. So once again, we have the center of mass at the center, or the geometric center of this pendulum rod. So it's L over 2, L over 2. And then I also just break up the forces over here, the reaction forces at the joint in Fx, Fy, but we can also denote it as F psi, F eta. Additionally, we still have the weight acting over here, which is then broken up into its two components. So mg cosine 30 degrees, mg sine 30 degrees. And over here, I added two accelerations as well. So previously we said that this acceleration inward is 0. This is still valid for the initial case, since we're starting from a 0 velocity. So this term will basically be 0. But this L over 2 phi 1 double dot will not be 0. Okay, so this is just information that is once again given, the same as the previous case. And now we also specify some sort of a driver over here. So we have phi 1 double dot, which is equal to 2 pi over 60 radians per second squared. So we specify what the rotational acceleration of the system must be. But in order to get that rotational acceleration, we have to have some sort of a moment over here that's going to instigate that motion. So we first just start with phi 1 double dot equal to 2 pi over 60. If I integrate it once, I'm going to get the rotational velocity. So that will then be phi dot 1 t, and that is equal to 0 plus 2 pi over 60 t. So this 0 is simply because I start from rest for my pendulum rod. So I end up with 2 pi over 60 t over here. You can also denote it as pi over 30 t, that's fine. And if I integrate this one more time, then I'm going to get phi 1 of t, which is then the rotation angle, equal to minus pi over 6 plus pi over 60 t squared radians. And this value over here is the initial angle that I have, minus pi over 6. Okay, and then, yes. So for this specific problem that we're looking at, this value is given, and then you would be expected to find the moment or the torque that causes this rotational acceleration. With regards to the starting angles, we do need to give you some sort of an initial condition as well. So if we would probably say it has to attain a 2 pi over 60 radians per second square rotational acceleration, it starts from rest at an angle of minus 30 degrees. Then you have all of the initial values at your disposal to actually calculate and integrate these functions. Yeah. Okay, and then we also have the x1 and y1 initial coordinates that we got previously as 0.26 meters and minus 0.15 meters. And then we can once again go and calculate the moment equilibrium about point A. Once again about point A, because we don't know what these reaction forces are, so it just makes the calculation a bit easier. So if I do that, then I say sigma MA is equal to IA phi 1 double dot, and that is then equal to this 1 over 3 to 0.6 squared 2 pi over 60. So I get this value on the right hand side. And then on the left hand side, I just have to go and add up all of the moments caused by the forces. So since I have this resultant moment, or this input moment over here, it's going to be n plus what I previously had was this negative moment caused by this mg cosine 30 degrees over here. So I just have to place that in as well, and then this is the calculation that I do on the left hand side. So if I combine the left hand side with the right hand side, my moment at the end should be 5.1226 Newton meters. Then I can also just go and do moment or force equilibrium to calculate the force in the xi direction, in the eta direction. So this is fairly straightforward with regards to the given acceleration. So I just break my accelerations up into the tangential and the radial parts. Then I can calculate f psi, which is 17.1 newtons, and f eta, which is 9.81 newtons. And then once again, I can just relate them by transforming them. So I'm just using that angle that is given. So fx should be 0.0314, and fy should then be equal to 19.674 newtons. Okay, so I see we do still have some time left, so let's maybe jump into the second example. Okay, so we now looked at PR underscore B, so that was our undriven pendulum rod. Next up, we want to look at PR underscore D. And I'm once again just going to perhaps close all of these. And I'm also going to type in clear all, close all CLC. And then we can reopen the PR underscore D input files. Okay, so firstly for inanimate, I changed some of the minimum and maximum values over here. So previously I used -1 and 1. I can actually make it a bit smaller, maybe -0.75 up to 0.75. So that will just give me a smaller window to actually see what the animation looks like. But in this case, since I now have some sort of an input driver motor, in that case, I then have to use Y min, Y max, and I'm going to use -0.75, 0.75, because this thing can actually go to the top and rotate around in the clockwise direction, or in the counterclockwise direction. Okay, so once that is done, then I go back to bodies. So you'll see that everything remains exactly the same, which I have over here. Over here, I just commented out this b1.r underscore d. So if you don't specify it, it's in any case going to take it as 0, 0. So I just commented that out. But everything else remains the same. I didn't actually change anything on the body. Its mass properties, moment of inertia properties, all those things remain exactly the same. If I then go to in forces, you'll see that now I have S1, which is equal to a force structure. The type is then weight. So this is the same that I had previously. I just want to double check. I think this might be one where we actually provide the force and we want to measure the kinematics. So this isn't actually the inverse dynamics problem. Let me just check if I go to infunct. Okay, yeah, so sorry, I think it's actually PR underscore E that we want to look at. Underscore D is then if we were to give it a force as input and we want to measure what the acceleration is. So I'm just going to reopen it over here. So this one also uses a torque, but we can actually just comment that out some. What I'm going to do is under the inForces.m file, I'm just going to say forces is equal to S1. I can maybe comment this out. We can use it at a later stage, but for now, I'm just focused on S1. So I just want the weight, and then I want to specify some sort of a driver that will ensure that I get that rotational acceleration as well. So if I now head to infunct, you'll see now where we previously had an empty list. In this case, we now have a function that I specified over here, f1, which is then this funct underscore struct, and I specify it as a type A function. So this type of function you'll find under, I think if we head to appendix B, right, so over here they give the different types of functions that we have. So for type A, we have C1 plus C2t plus C3t squared. If I go back to the calculations that we did for this problem, you'll see that for phi1 as a function of t, so this is the function that we need to specify. We have a constant plus 0 times t plus pi over 60 times t squared. So what we essentially have over here is then a type A function. And for that, we just have to specify the type, and we have to give the coefficients in as well. So the coefficients will simply be C1, C2, C3, and we're going to separate them just by a space over here. Okay, so that's exactly what we did over here. We just have minus 0.523, so this is the value that we can calculate. If we use that minus pi over 6, then 0, because we don't have anything multiplied with t, but we do have something multiplied by t squared, and that was the pi over 60, I believe. Which is then 0.0524 that we have over here. Okay, so now I've specified the function that I need to use. Now I just have to call the correct joint that I'm going to use over there. So in this case, where we previously just had a revolute joint, now I specify a relative rotation driver over here. And the reason for that is I want to constrain or create a driver constraint on the actual rotation of the system. So I specify it as a relative rotation driver. So for this type of joint, I need to give it the two body indices in. So the first body index is body 1, so that is the pendulum rod itself. Then I also have the second body index, so that is simply 0 or ground. So the relative rotation will be between ground and body index 1 or body 1. Yes.
What order you put it in?
No.
0, 1, 1.
No, so it doesn't make a difference. I think it might just have an effect on the sign, if I'm not mistaken. But overall, your magnitudes and everything will remain the same. So yeah, that's fine. And then lastly, we also have j2.ifunct. So now I just have to go and call the actual function that I specified. And in my case, I only have a single function, f1. So its index over here is just 1. And once I did all of that, I just combine it in my joints list over here. So endpoints will remain exactly the same. So I have point 1, 2, and 3, which I specified previously as well. And my in-u vectors is still an open vector over here. So I don't have to worry about any. Once all of that is then set up, now I can go and run DAP again. It will once again ask what the folder is that contains the model. So I'm just going to say br_e. Then it says, do I want to correct the initial conditions? Yes, I do. And we can see that I still get the correct coordinates and the velocities over here, so that's fine. And then I can also do for the final time, maybe again 3 seconds with another reporting time step of, let's say, 0.01 seconds. Okay, so then the number of function evaluations we can see is 93. So it converged quite quickly, considering the previous version that we had was 603 function evaluations. So once that is done, I can just animate it again. And if I click any button over here, we can see here at the start, it's actually a bit difficult to see, but it's still in the process of accelerating over here. So let's see if I maybe make this larger. So you can see it's starting to move, but it's moving fairly slow. Yeah, so it might not have been the best choice to maybe use 0.01 seconds. I think then it's going to run for quite a while. But we can see now that that this thing is starting to move. I just want to see until how long it takes for this thing to actually reach a reasonable velocity. Okay, so it does seem to be taking a while. I just see if I maybe can cancel this, close this one, and let's perhaps try it again with a bit of a more coarse time step. So if I just type in DAP again, PR_E, yes, I want to correct it. Final time we can make 3 seconds. And let's maybe use 0.1 over here. Then animate. Okay, now we can see a bit better motion of this system over here. So it started fairly slow and then it started to accelerate. So we can now go one step further and say, okay, we want to actually see what a full rotation is going to look like. So if I perhaps do DAP PR_E, corrected initial conditions, let's use 30, and let's maybe still use 0.1. Okay, so now we can see it also took longer to solve the problem because of the larger time step, the larger final time that we have over here. I just go to animate again. We run this one. Now we can perhaps better see this motion of this thing. So it started relatively slow. As it's moving, it's now sort of picking up speed. And we can see it's also now rotating in the counterclockwise direction. So it was a good choice to make the upper Y limit 0.75 so that we can actually see how this thing rotates. Okay, so based on this motion, we also expect to see perhaps some oscillations in the X and Y points. We will also perhaps just have a look at how the angle changes, the orientation angle. So what DAP BC does is instead of cycling between positive and negative values for the angles, it will actually just continue to add to that angle. So as it's rotating, you will see perhaps large angles, something like 1,200 degrees at the end. That's mainly just because it doesn't cycle between plus and minus, it just continues to add to that angle. Okay, yeah, so now it's stopped, so we can just close this. And now we can type in post, just to load all of the post-processor outputs. And then since we also still have that post plot available, since I specified it originally, I can just go and specify or run this code again. Just to quickly look at the Lagrange multipliers as well. So you'll notice now we have a 301/3 matrix over here. So if I go in, the first 2 columns that I have over here still specify the kinematic joint, the revolute joint that I have. However, the third one now imposes the actual moment that I need for that relative rotation driver. And if I look at the very first value, 5.1226, if I go to the values that I calculated over here, you'll see that the moment over there was also 5.1226, so that means it initialized correctly. And then I can also just go and check out the forces in the fx and fy directions. So in the fx direction, it's 0.0314. If I go over here, I can see that it's now minus 0.0314, so exactly the same magnitude still. And then fy will be 19.674. If I head over here, I can see that I also get minus 19.674 over here, so that's correct. Okay, so then I can just run post plot, see what I get out. Okay, so lastly, just looking at the angle that I have over here, we now know that we started over here at around minus 30 degrees. And if we now continue upward, so because it's moving in a counterclockwise direction, this angle is then going to go positive, and it's going to continue to add to that angle until I get this value over here, which is 46.4 radians. I can also just go and convert to degrees if I want to, so I can just use times 180 over pi. Then you can see what it looks like in degrees. But the angles are as expected, it's going to continue to increase. Then on figure 4, if I look at this one over here, so this was basically the velocities that I plotted over here. And we also see that the black line is then the resultant velocity. And this is more or less also what I expect. I can see that it starts with relatively small oscillations, and as it continues, the frequency increases. So the distance between these sinusoidal waves decrease, and the amplitude increases as well. So that is what I expect since I have acceleration in my system. And then we also have this line over here, which is simply the magnitude, or the magnitude of the velocity, or the speed, if you will. And then we can also go and look at figure 3. So that was the Lagrange multipliers 1 and 2. So that is then simply the reaction forces that we plotted over here. I can also perhaps go and do the Lagrange multiplier 3, see how my moment changes as well. I'll do that in just a moment. Let's perhaps first look at the coordinates. So we can see over here as well, the x and y coordinates first have a relatively large period, so it's a smaller frequency, and then as it continues, this frequency increases once again. Okay, so this is once again what we expect for this system. And I think it didn't close this one. Just do that. And then finally, we can also look at the position of the center of mass of the system. And we can see that indeed, if we set the axes equal to one another, we can see that it does have this circular range over here. So that's also correct. Over here at the start, which is more or less over here, we can see that the points are a bit more, a bit closer to one another. So that is simply because we have acceleration over here at the start. So the initial time steps over here means that we have a smaller velocity, and hence these positions are a bit closer to one another. Okay, so if we perhaps look at the plot of the moment that we then get, and we can say, let's create, just going to call it figure 1. And then we can plot it as a function of time, and this will once again be the Lagrange multipliers across all the time steps, but for the third driver constraint reaction forces, or the reaction moment. And then I can perhaps also use a black line to denote that. Okay, and there we can also see the moments that are then being caused by this, this rotational acceleration that I specified. Okay, so if you are perhaps interested in, let's say, the speed or the location of a specific point, you'll see if you scroll down over here, after R, you also have RP, RPD, RD. So each of these can also be plotted. So you once again have your time steps over here, then you have the number of points. So you have to specify the specific point that you want to plot, and then whether you want to plot it in the X and Y direction. Okay, so you're more than welcome to go and have a look at some of those plots as well. I think just to make things a bit easier, I'll also upload this post-plot file or this script to ClickUp, so then you can maybe download that and then just copy it over to your DAP BC workbench and play around with that a bit more. Right. Okay, so I think that more or less concludes what we wanted to do today. Are there any questions with regards to DAP BC so far? Okay. Right, so I think next week we'll just look at 2 other pendulum rod examples as well, and then the lecture after that we're going to jump into application examples. So over there we're going to look at some spring mass damper systems, contact forces, how we can model those kind of things as well. But for now, I think this more or less covers everything that we wanted to look at for the dynamics and kinematics of a simple pendulum rod. All right, so thank you. See you next week.
See that the moment completely